Welcome back. In this lecture, we'll be discussing single-phase gas reservoirs or dry gas reservoirs. You might remember when we were discussing the different reservoir types in Chapter 1, we looked at in Figure 4 various types of reservoirs. And the single-phase gas reservoir was on the right-hand side of that figure, as you can see in this slide. Now, what we mean by a single-phase gas reservoir is that during the life of the production, the hydrocarbon phase in the reservoir itself will remain as a single-phase gas. Now, there might be some liquid that will be produced on the surface as the gas is brought through the production pipe and then into the separating systems. But when we refer to single-phase gas reservoirs, we're talking about what remains in the reservoir. And this figure will show that. Again, it's to the right of the cricondotherm, and so as you can see, a constant temperature process is what we have during the production phase in the reservoir itself, and it will stay then as a single-phase gas. Some of the important data that we need as reservoir engineers to make calculations are shown in this slide. One of the first things that we'll do is try to map the reservoir with the seismic data. We talked about seismic information in a previous lecture. But getting the seismic data will allow us to map out the extent of the reservoir, the boundaries of the reservoir, and also the thickness in the various locations, as you can see on this slide. This is a fairly typical diagram that one would generate from seismic information. Once we have the areal extent and the thickness of the reservoir, then we simply multiply those values together to give us an initial estimate of the bulk volume of the reservoir itself. Another source of data that we need is what we call core samples. We typically will take, as this diagram shows you, 1 inch in diameter, about 2 inches long, samples of the rock structure itself, and we'll do that at every 1 foot intervals in the pay zone. We'll bring those core samples to the surface, and we will measure saturations. We will measure the porosity, and so we'll get a feel for how much of the core contains water or gas, or in the case of an oil reservoir, oil. And when we measure those saturations, we give them a symbol of S sub O for oil, S sub G for gas, S sub W for water, as we talked about in Chapter 1. The letter I is sometimes added to those subscripts to denote the initial value of that phase. The recovery factor itself is dependent on the production mechanism for the reservoir. And in the dry gas reservoirs, we'll talk about two main mechanisms. The first is what we refer to as gas drive, which is simply the expansion of the gas as we drop the reservoir pressure during the life of production. The second is water drive, and that will be due to encroachment of water from an aquifer that is nearby the hydrocarbon deposit. In the case of a gas drive reservoir, there is typically neither water encroachment nor water production, or a very limited amount of water production, and we will refer to this kind of a reservoir as a volumetric reservoir. We'll talk in this chapter about two methods of calculating the initial, or getting an estimate for the initial hydrocarbon in place. The first of these methods uses geological, geophysical, and fluid property data to estimate the volume of gas. The second method uses the material balance equation that we discussed in Chapter 3 in a previous lecture. The first method of calculating hydrocarbon in place using the geological, geophysical, and fluid property data involves measuring the thickness of the reservoir with seismic data, getting an aerial extension, getting core samples, measuring the saturations. The standard cubic feet of gas in the reservoir is given by this expression in this first slide here. V sub G will be the gas pore volume. If we divide that by the gas formation volume factor that we defined in chapter 2 of the text, we can express the gas pore volume in standard cubic feet. The gas pore volume is related to the bulk or total volume of the reservoir with the average porosity and the average connate water saturation. In this expression 4.1, you can see the expression for capital G, the gas in place. It's common, V sub B, the bulk volume of the reservoir, is commonly expressed in acre feet. And so with that measurement that we get from the seismic data of the aerial extent and the thickness of the reservoir, we can multiply those two together to give us that bulk volume, and that's why we express it in acre feet typically. In many gas reservoirs, particularly during the development period, the bulk volume of the reservoir is not known. And so in those cases, we will calculate what we call the initial gas in place on a unit basis. So typically, that will be on a 1 acre foot basis. And the equation in this slide, equation 4.5, is the initial standard cubic feet of gas in place on a per acre foot basis. For a reservoir under volumetric control, the gas remaining at abandonment is given by equation 4.6, as shown in this slide. If we then take a look at the unit recovery, which is the difference between the initial gas in place and that which is left at the abandonment pressure, you can see in equation 4.7 an expression for that unit recovery. Notice that it's just our constant 43,560, which is the amount of square feet in an acre, times the porosity times 1 minus the water saturation, and then times the difference in the formation volume factors at the initial pressure and at the abandonment pressure. The fractional recovery, or recovery factor, is expressed in percentage of the initial gas in place, and it's given by equation 4.8 here in this slide. Now let's take a look at calculating the unit recovery from a gas reservoir under water drive. The initial conditions, connate water is expressed here as 43,560 times the porosity times the water saturation. The reservoir gas volume then is that times 1 minus S sub Wi, and the surface units of gas then would be that expression divided by B sub Gi as expressed here in this slide. In many reservoirs under water drive, the pressure suffers an initial decline, but then as water comes into the reservoir from the nearby aquifer, as water encroachment, the reservoir pressure will begin to stabilize. At this point, the abandonment pressure then will be that stabilized pressure. And you can see in the bottom of this slide an expression for that reservoir gas volume at that abandonment gas saturation, S sub GR. The unit recovery then, in this case, would be given by equation 4.9 in this slide, and the recovery factor by equation 4.10 in this slide. If the water drive is very active, and as a result there's essentially no decline in the reservoir pressure, the unit recovery and the recovery factor become what they are in the equations 411 and 412 expressed in this slide. Let's look at an example calculating the initial gas reserve of a 160 acre unit in the Bell gas field by volumetric depletion and under partial and complete water drive. In this slide, the average porosity, the connate water, the residual gas saturation after water displacement is given, formation volume factors for the gas phase, the aerial extent, and the net productive thickness of the reservoir is given as initial data. The solution, if we look at the pore volume, is 43,560 times the average porosity times the areal extent and the thickness of the reservoir. And that gives us this figure. The initial gas in place then, I simply take that figure, I multiply by the water saturation, 1 minus the water saturation, and divide by the formation volume factor. And that gives me 8,860 million SCF of gas in place. Gas in place after volumetric depletion to 2,500 psi is given in this next line, and that's simply the initial gas, the pore volume, times 1 minus the water saturation divided by the formation volume factor at 2,500. The gas in place after volumetric depletion to 500 psi is the same expression, but divided by the formation volume factor at that pressure as shown on this line. The gas in place after water invasion at 3250 psi is given by this with the residual gas saturation and the formation volume factor, and at 2500 is given in this next line. So if we take a look at the initial reserve by depletion to 500 psi A, and then by the water drive at 3250 and at 2500, we see these three different values for the initial reserve, or the gas expected to be recovered at these different, under these different situations. You'll note that the recovery factors calculate to be 85% for the depletion by gas drive down to 500 psi A, 65%, and 56%. And you can see then what the effect of the water encroachment is on the recovery. The water encroachment retards the pressure drop and doesn't allow the gas to expand as much, and therefore we don't produce as much as the gas when we have that water drive. Now let's look at calculating these same kind of values, gas in place and recovery factors, using the material balance equation that we looked at in Chapter 3. The general material balance equation was derived for a gas reservoir in Chapter 3, and it's given here as equation 310. For most gas reservoirs, the gas compressibility term is much greater than the formation water compressibilities. And so the second term in the equation in 310 becomes negligible, and the equation reduces then to equation 413, as shown in this slide. For a volumetric gas reservoir, equation 413 can be reduced to a simple application of a straight line involving the gas produced, its composition, and the reservoir pressure. So if we take a look at equation 413 and expand that by placing in the definitions of B sub G and B sub GI, we end up with equation 415, noticing that some of the equation terms in the equation will cancel. We'll end up with this following equation, equation 416, which suggests that if we made a plot of P over Z versus G sub P, the gas produced, we would see a straight line, with the slope being minus pi over ZIG and the intercept being pi over Z phi. You can see on this slide then a depiction of that kind of a situation. We have the P over Z plot versus the cumulative production. The circle dots and the line drawn through those dots represent that plot, P over Z versus G sub P. If you look at the curve just below the P over Z versus G sub P plot, you'll see pressure plotted versus G sub P. Notice that it has some curvature, and it will not be a straight line. The top curve represents a situation where we have water drive in the reservoir, and it, again, is not on the straight line that we would predict with a volumetric reservoir.